Okay, so welcome back to Meteorology 121 Fall Semester 2017 video series. Today we will continue thermodynamics. We covered this topic back in, must have been early October this semester. We didn't quite finish. We got some other topics that we got to get to following from the things that we did cover. So in front of you here you see a list of topics we've already covered. So you should be able to go back in your notes and assignments and material from when we covered thermodynamics earlier in the semester to tick off these topics that you see here. So we'll just go through them real quick here. The ideal gas law, PV equals nR star T. The dry air gas law, P equals rho R dt. We'll be reviewing these equations in the next slide, so we'll get to that. Molecular weight of dry air, remember this is when we calculated by adding up the partial pressures for each major constituent in dry air, the contribution to pressure and molecular weight due to each constituent, and we came up with a value of 28.97 for the molecular weight. That was a assignment problem. First law of thermodynamics, the change in heat in a parcel goes towards two major processes in dry air, work and internal energy. Adiabatic process is one where no heat is added. The dry adiabatic lapse rate is the rate of temperature change with height that a parcel experiences if it is undergoing an adiabatic process. And potential temperature, this is that temperature that is conserved for adiabatic motion. So we'll be reviewing these points now and as we continue on in thermodynamics. So here's a table that summarizes the points we just made in the previous slide. So you'll see here how it's organized. We have it by topic on the far left column, the key equations involved in the middle column, and some notes that correspond to each entry on the right here. So these are all, again, review from when we covered thermodynamics earlier, but let's just go through these quickly just so that we can get a little bit more of a refresher. So for a single gas, we can apply the ideal gas law, and this is a relationship that how can you say it? It basically relates three thermodynamic quantities that must be satisfied, mutually satisfied, such that this equation holds, the ideal gas law. So the three quantities are the pressure of a volume of air, let's say, the volume of the air itself, the mass per unit mole, molecular weight rather, the mass per unit molecular weight, which is the number of moles of gas, N, R star, which is the universal gas constant, and T is temperature. So the three main quantities is that for a given mass of gas, the temperature, the volume, and the pressure must be related in such a way that this equation holds. So again, here are the quantities we just summarized here on the right here. Now this is for a single gas or in any gas, that is, as long as it's in an ideal state, and one can go back to a more fundamental treatment of thermodynamics to review what we mean by an ideal gas. But the atmosphere is in an ideal state, so we can apply it to the atmosphere. The only thing with the atmosphere is that it's a mixture of gases. So once you bring into play that we've dealing with a mixture of gases, we need to apply Dalton's law of partial pressure. In that case, sorry, the subscripts didn't quite come out here, but this is for an individual component of a mixture, component I, let's say, the pressure of that component times the volume is equal to the number of moles of that constant times R star T. So the less the number of moles, the less the partial pressure. So then that's how it really kind of equates. And then with every portion of the gas, say air is a mixture of many different gases, but you just take the number of moles of each constituent, calculate the partial pressure, and then add it up, and that's the total pressure. And that's what you see here. The pressure of the gas is the total sum of the partial pressures. So with that, one can review that the molecular weight of dry air is simply the weighted average of the individual molecular weights of the constituents weighted by the number of moles of that constituent. That's also, again, from the Dalton's law of partial pressure, weighted by the partial pressures, or it can be weighted by the volumetric fractions through some other mass. So basically, it's a weighted average of the constituents gives you the molecular weight of dry air, and again, that's equal to 28.97. You can review that. Okay, so that brings us to new material, Lecture 18. So now we're going to pick up where we left off with thermodynamics. We're going to use the things we just reviewed moving forward now. So that's why we wanted to present that, so you have some review before we launch into this new material. Okay, so uploaded to Canvas were lecture notes for Lecture 18. So you'll want to have these handy as we go through these slides, so that as we go through these slides, these are a lot of cut and paste from those lecture notes, but we didn't cut and paste everything. So you'll want to have these on your side to just flip through as we go through some things. But we'll go through the main points here. So right away I see that some of the editorial things in the notes didn't quite come out here on the slides, so we'll have to work around that, but I think we can do that. Okay, so what we're going to do here is derive something called the thermodynamic equation. Where's my little highlighter? That's what I like right there. So the thermodynamic equation is from the first law of thermodynamics, and what this is a rate equation for temperature. So you may recall what we've seen so far in the class is we have a rate equation for the wind velocity, meaning the momentum equation, dv dt equals minus 1 over rho grad p, the pressure gradient force, the Coriolis force, all that stuff. So we have one for velocity. We have one for mass through the continuity equation, mass conservation, d rho dt equals minus grad dot mass flux. You can refer back to that. What else do we have? We have one for let's see, any species concentration, change in, for example, pollution concentration equals the mass flux of pollution concentration. So anyway, there's rate equations out there. And so to get one for temperature, we use the first law of thermodynamics, because this is our conservation equation for heat. So as you see here, heat added to a parcel is change in internal energy plus or minus work performed or by or on the parcel, depending on the sign. The other alternative form, like we've talked about, is the dp dt minus alpha dp. Now, if we divide through by dt on both sides, you see that we can say the rate of change of heat added to a parcel goes to the rate of change of internal energy minus the rate of change of work performed, or the enthalpy. We call this alpha dp dt. So that's just differentiating by dt through the equation. And just through rearranging the equation, we can bring the dt on the left-hand side, and we got this equation here. So now, the trick is, remember, dp dt, that's omega. Remember we worked with omega in a previous lecture. That's just the pressure velocity, the rate of change of pressure following the motion. If we were to plug that into the equation, remember what dp dt is omega, and omega is minus rho gw in a hydrostatic atmosphere. Okay, so plugging in minus rho gw for dp dt into this first term on the right hand side, you can see that the alphas and the rhos cancel. Okay, and we get minus gamma dw here. So hopefully you can see that through this mistake editorial here from the porting into the software here, but you'll have your notes so you can see gamma d is G over Cp. So that's where the gravity from the omega and the Cp in the denominator get absorbed into. So this is an interesting equation. And then you got the diabatic term, what we call the dq/dt, the heat going into and out of the parcel here on the right-hand side. So this, yeah, like I said, this is an interesting thing. Following the motion, the rate of temperature change following the motion is due to any heat absorbed or released by the parcel between the parcel and environment. For example, if heat comes in, the temperature will rise. If heat is released, dq/dt is negative, temperature will decrease in the parcel. That's easy. What's the other thing interesting here is the adiabatic term. So if you have rising motion, that's W greater than 0, gamma D is negative 9.8. Rising motion will therefore give rise to a temperature drop, because gamma D is positive, W is positive, got the negative sign out front, dT will be negative. So rising means cooling of a parcel, as we know. Sinking means warming of the parcel, as we know. So we got both things. The diabatic term, meaning for non-adiabatic conditions, diabatic heating, and the adiabatic term, meaning that if there's no heat released or absorbed by the parcel, you still have a temperature change, because rising motion will cool adiabatically, sinking motion will warm adiabatically. And that's exactly what we're saying here in this slide. I just took that equation. Let's emphasize what we mean by the adiabatic term and the diabatic term. The adiabatic term is minus W gamma D. The diabatic term is dq/dt, the heat released or absorbed by the parcel. Okay? The same points we just made. Cooling due to adiabatic expansion as parcel rises, warming due to adiabatic compression, meaning as the parcel sinks. We know that happens. We've been talking about that, and maybe from previous meteorological classes, you talked about things such as Santa Ana conditions where sinking motion gives rise to compressional heating, which brings really warm weather. And also here, the warming due to heat released or absorbed by the parcel due to the diabatic term. And we say some stuff about radiation being probably the most common process by which this happens. So sunlight gets absorbed by a parcel, heat coming in from outside, the temperature will warm. And vice versa for radiation released by a parcel, say from infrared radiation released by the parcel, then that would cool the parcel. So expanding the Lagrangian form of the equation into its Eulerian form, we get as follows here. So total temperature d with respect to time is the partial plus v dot grad t, and that equals, as we saw in the previous slide, to the adiabatic term and the diabatic term. Okay, so moving the v dot grad t on to the right hand side, that gives us the local change in temperature with time at some point within a column. Now we're in an Eulerian frame, so this is at a fixed point, is equal to the advection terms, the adiabatic term and the diabatic term. So that's where we get advection into this. So at a fixed point, air from outside of a different temperature can blow to that location and change the temperature. So this is what we get when we have an Eulerian frame of reference. Remember, we have the advection terms that get put into it. Remember what the advection terms expand to: the zonal part, the meridional part, and the vertical part. Okay, so you can have advection from all three directions. Now, taking this and regrouping terms, we can see kind of an interesting thing here. So dT/dt, the rate of temperature change at a fixed point, is equal to horizontal advection, okay, u dt dx minus v dt dy. Remember, taking from the v dot grad t, just taking the first of these two and putting them here. We call that horizontal temperature advection. Then if we take the vertical advection term and define T/T/dz as gamma. Now this is called the environmental lapse rate. It's the actual rate of temperature change with height of the atmosphere. So remember, we differentiate that between gamma d, which is what a parcel experiences in terms of temperature change following the parcel up and downwards through in adiabatic ascent or descent, which is gamma D, and then gamma, which is the actual temperature change of the environment itself, regardless if there's rising motion or not. It's just whatever the state of the temperature is with height at a given column, okay? So when we put the two together, the adiabatic term from our previous equation plus the vertical advection term from now the expanded form when we put this in an Eulerian frame, we see that this vertical motion term has two parts. It has a vertical advection part and an adiabatic term part. And when we group it, we see that the determining factor, determining whether temperature rises at a fixed point within a column, is the difference between the environmental lapse rate and the adiabatic lapse rate. So gamma minus gamma D. This is an important quantity. It actually relates to atmospheric stability, as which we'll see now. So let's proceed forward with looking at this term in particular and learn more about it. So to summarize what we saw in the last slide, horizontal advection term, the net temperature change due to vertical motion. This combines both the vertical advection and the adiabatic term and the diabatic term. Like we said, this quantity gamma here is called minus dTdz. It's called the environmental lapse rate. It represents the actual rate of temperature change with height in the air column at some location in time. For example, as we measured by a radiosonde. So yeah, this is what is plotted on a skewed T every time a balloon is launched, say from a radiosonde site, Oakland sounding, various other sounding locations around the world. They plot the actual temperature change with height as measured by the balloon, by the radiosonde. And that will be what we mean by gamma, which is the environmental lapse rate. The dry adiabatic lapse rate, on the other hand, is the rate of temperature change of a parcel undergoing adiabatic warming and cooling due to vertical motion. These two lapse rates are used to define the typical buoyant atmospheric stability criteria: neutral, stable, and unstable for a dry atmosphere. So likely you've covered what neutral, stable, and unstable means. In parcel theory, a neutral atmosphere is one where the parcel has the same temperature as its environment. A stable atmosphere is that upon vertically lifting a parcel, the parcel becomes warmer than its environment, and cooler than its environment, and sinks back down. And an unstable is then upon adiabatic uplift, the parcel then becomes warmer than its environment and keeps rising if it's unstable. So the cutoff between neutral, stable, and unstable is when gamma is on either side of gamma D, as we'll now show. Okay, so as you see, this slide didn't come out too well. Definitely some porting issues going from my Microsoft Word document into, or I'm sorry, PowerPoint document going into this, but please print out the lecture notes so that you have these alongside of viewing this, because inside the lecture notes it'll be correct, but just didn't port over very well, as you see, into the screen. So, but we'll proceed. This is just an illustration again of what we mean by neutral, stable, and unstable, especially emphasizing how that neutral, stable, and unstable relates to the environmental lapse rate and the dry adiabatic lapse rate, gamma relative to gamma D. Okay, so let's go ahead and just draw this out. So what I'll do is do that, and then for neutral here, let me see if I can't get my thing here. We might do something like this, where here's the surface, and this is Z going upwards, and we'll plot temperature as a function of height here. So maybe just kind of visualizing this here. Get this going here. T will increase going this way. Okay, so for a neutral atmosphere, temperature will have the gamma, the environmental lapse rate, actual way temperature changes with height, is going to match the adiabatic lapse rate. And I'll kind of put a little dashed line here and I illustrate that, and we'll call that gamma D. So when gamma equals gamma D, that's what we mean by neutral. Okay, What this means is that as a parcel rises, let's say, it's going to cool adiabatically. So it'll drop in temperature according to the gamma, the dry adiabatic lapse rate. But you see that if the actual lapse rate is equal to that, then the parcel will have the same temperature as an environment and will just not accelerate as it rises upwards. So you see vertical motion is maintained, no vertical acceleration. Okay, so a neutral atmosphere is one that doesn't have any vertical acceleration to it. And so we'll actually work a little bit more with that in 121b, but that's what we mean by neutral. Okay, stable, you can do the same diagram here. Temperature increasing to the right, and then we got height increasing vertically. Okay, so let's draw our gamma D. Okay, okay, and in the stable atmosphere, gamma is less than gamma D, which that means is that the rate of cooling is less with height than the dry adiabatic lapse rate of cooling. So to draw that, we'll draw a line that, yeah, it cools with height, but maybe not at the same rate, maybe at a lesser rate than gamma D. So that would be what gamma is. In this case, you know, gamma, this would be a situation where gamma is less than gamma D. Now what you'll see is that as the parcel rises, it cools adiabatically, but it is cooler than its environment and would sink back down. This is where you have negative acceleration or buoyant deceleration in the opposite direction of the vertical motion. So this will eventually have the parcel sink back down if the acceleration in the opposite direction persists in time long enough. So this is a stable situation. An example of an extremely stable situation, as you can see, is a temperature inversion where temperature rises with height. That would be a situation where the lapse rate is much, much less than the adiabatic lapse rate. So that's an extreme example of stability, the temperature inversion. Here's the situation for the unstable atmosphere. Again, temperature doing this. Let's draw our dry adiabatic lapse rate. Getting a little sloppy here, but that's fine. And then, as you can imagine, if we do this, that's an unstable atmosphere. The rate of temperature change with height in the environment is cools at a greater rate than the dry adiabatic lapse rate. Then gamma is greater than gamma D, and this would give rise to vertical acceleration of rising motion. As a parcel rises adiabatically, it cools according to adiabatic lapse rate, but you can see it would be warmer than its environment, and it would be accelerate. You'd have buoyant acceleration because it's warmer than its environment. Okay, so that's just a review of stability, and it relates to how gamma and gamma D intercompare with each other. So when the environmental lapse rate is different than the dry adiabatic lapse rate, we have either stable or unstable conditions. If they're equal, it's neutral. When gamma is less than gamma D, stable. When gamma is greater than gamma D, unstable. Okay, so now let's see the consequences of a neutral, stable, or unstable atmosphere on the temperature change experienced within the column. Okay, so we know that neutral atmosphere, gamma and gamma D are equal to each other. For a stable atmosphere, gamma is less than gamma D, and for an unstable atmosphere, gamma is less than gamma D. What we have here is 3 examples of the consequences on temperature within the column in those situations. We have 1 for neutral, and we have 2 for stable. One in which we're going to say that the parcel is rising in the column, and another where the parcel is sinking in the column. And let's see what the consequences are on temperature in that situation. Now remember the term in the Eulerian equation for temperature changes we saw in 2 slides previously. For the effect on the temperature in the column due to vertical motion is, get the highlighter here, equated to W times the difference gamma minus gamma D. Okay, so as we can imagine if the atmosphere is neutral, gamma is equal to gamma d, and that would mean regardless of the vertical motion, there's going to be no temperature change, because as a parcel rises, it's going to cool at exactly the same rate as the temperature already is cooling with height. So there's going to be no temperature change. You're not going to have any situation where the air as it rises is going to take on a different temperature in its environment and thereby change the temperature in the column. So neutral means no temperature change in a fixed point within a column. But let's see what happens when we have rising motion in a stable atmosphere. So with the stable atmosphere, gamma is less than gamma d. So here's the rate, the actual temperature change with height. Here's what a parcel experiences. So if we start at the surface and rise and have rising motion, initiate rising motion, the parcel is going to cool according to the dry adiabatic lapse rate here. You can see what that means is that is in effect bringing cooler air upwards to a fixed point within the column relative to the air around it. Okay, so yes, the parcel will sink back down, but it's also, as it's rising, bringing effectively cooler air upwards, because the cooling of the parcel as it rises upwards is causing a point within the column to get colder because the air is cooling as it rises. So let's see what that means mathematically. Is W is greater than 0, meaning rising motion. Gamma minus gamma d is then less than 0 because gamma d is a bigger number than gamma in this situation. So the quantity, when you multiply a positive W times a negative gamma minus gamma d, you would get dt dt, the rate of temperature change with time would be negative. So because W is positive, gamma minus gamma d is negative, a positive times a negative is a negative, that's going to give you a negative temperature change or cooling in the column. Likewise, if the parcel is sinking in the stable environment, the parcel is going to be rising in temperature according to the dry adiabatic lapse rate, but that's going to then bring you a warming of the column relative to the air around it, because in a stable atmosphere, gamma is less than gamma d. When W is less than 0, gamma minus gamma d is less than 0, a negative times a negative is a positive, you would get warming of the column in that situation. So in a stable atmosphere, rising motion is generally associated with cooling of the column. Sinking motion is associated with warming of the column. And this is exactly what we're saying here. So you can see the points we made here, that a column of air will cool in a stable atmosphere if you have rising motion. In a stable atmosphere, a column will warm if you have sinking motion. We look at stable atmospheres because this is by far the most common case on the large scale, is that the atmosphere will be slightly stable. We're not doing an example here for unstable because this is a very uncommon situation that you would have unstable atmosphere persisting for a long time. That's a topic for another time. So this analysis works well with stable. Well, it's not. When you deal with unstable atmospheres, you have a different situation in a lot of ways. So we'll just stick with stable. For our emphasis is large-scale meteorology in this class, so stable atmosphere is what applies in general. Okay, stable. At large scale, rising motion is generally associated with cooling of the air column and sinking motion with warming. Okay, this will be something that comes into play as in next class 121B when we look at baroclinic systems. The adiabatic cooling of the air downstream of a trough has an effect on the dynamics of the storm system, and we'll learn about that. Okay, so potential temperature is another way of expressing everything we just saw. Let's review what we know about potential temperature from what we covered previously. Potential temperature through the Poisson equation is equal to temperature times this factor involving pressure. Remember what potential temperature is. It's the temperature at 1,000 millibars if an air were brought on through a dry adiabatic from some initial point along the dry adiabatic to 1,000 millibars. So you can follow along a dry adiabatic and go to 1,000 millibars and see what the potential temperature is. Each adiabat on a skew T is associated with a value of potential temperature. Okay, so you can look at a skew T to remind yourself, but potential temperature is then conserved in adiabatic motion. This is one of the good things about it, is that whereas temperature cools if you have rising motion and warms if you have sinking motion, the potential temperature will not change. Okay, and so this is another way of defining temperature through its potential temperature. It applies to an adiabatic situation where theta is constant. Okay, here's the equation, brings in this kappa parameter, RD over CP. Now taking d by dz of both sides of this equation and then doing a bunch of math, you can check on Holton on that, you get this relationship where the rate of change with height of potential temperature times a T over theta factor is essentially related to the difference between gamma D and gamma. So you can see that right now a neutral atmosphere, one where gamma D and gamma are equal, means d theta dz is 0. So that means constant theta is now the divider between neutral, stable, and unstable. Okay, so you can remember gamma D was before the divider. Now you can also relate that to potential temperature, where a neutral atmosphere is one where d theta dz equal to 0, because gamma D and gamma are equal in that case, and if you subtract them you get 0, d theta dz is 0. Okay? Okay, so let's do this. Again, sorry for the editorial issues, but this is the equation we saw previously, d theta dz times T over theta is equal to gamma D minus gamma. So we can then go through and just draw out what this means. So here we go, we got theta, sorry, I'm awful with my penmanship here. You get the point, right? Theta is increasing. Hold on, let's fix this. Let's erase that, that looks terrible. There, try again. All right, let's try to see if I can't do a little better job here. A little better. Okay, so theta is increasing to the left, C upwards. This would be neutral, straight up. Theta does not change with height. Okay, this is d theta dz equals 0. Okay. Here is stable, d theta dz greater than 0, and this would be unstable, d theta dz less than 0. Sorry guys, I am not good at this stuff. All right, there. You get the point. Okay, so just like gamma D could be used as a divider for neutral, stable, unstable, the cutoff d theta dz equals 0 can also be used as a cutoff between neutral, stable, and unstable. Okay, so let's proceed further in the notes now. So you may remember from lecture 9, you probably have to refer back to this, is that an increment in d theta is equated to an increment in dq. Remember, so for theta is, a change in theta is 0 when you have adiabatic conditions. Remember, potential temperature does not change for adiabatic conditions when dq equals 0, so that makes sense. If dq is 0, d theta's got to be 0, because for adiabatic conditions, theta doesn't change. All right? Now, that means for diabatic conditions, theta does change. So if you take the time derivative of both sides of this equation, the change in potential temperature, following the motion, thereby is non-zero if following the motion there's diabatic heat release or absorption by the parcel, okay? So following the motion, if it's adiabatic, you won't get any change in theta, but if there is some diabatic effects, you will get an increase or decrease of potential temperature, okay? So comparing 18.3 and 18.5, remember this is the other one for temperature d time, you see that you don't have this adiabatic term. Remember that for potential temperature, adiabatic motion means no change in theta. So you don't have the situation where you got to account for the temperature change of you have rising or sinking motion, because that's absorbed in the definition of theta. Theta will not change as you have adiabatic motion or adiabatic rising in the column, adiabatic sinking. The potential temperature does not change. Temperature does, potential temperature does not. That's what's stated here. So now, if you were to expand this equation into its Eulerian form, you can get the following equation on the right. So you have advection of potential temperature, diabatic heating or cooling, and that's what leads to a change in theta with time, okay? Note again that the term in 18.4, which is the temperature version of the equation, not potential temperature, but temperature, the term involving gamma d does not appear in 18.6, okay? This is why potential temperature is used a lot, because it absorbs a term and we don't have to really explicitly account for it because it's absorbed in the definition of potential temperature, okay? So finally, we can look at kind of the implications of cooling and warming of potential temperature for situations. Now, for a neutral atmosphere, remember, neutral atmosphere means d theta dz is 0, okay? The environmental lapse rate for potential temperature is 0, meaning that you have a dry adiabatic environmental lapse rate equals the dry adiabatic lapse rate. Here, if you have rising motion, the potential temperature is constant with height, but if the environmental lapse rate is already neutral to begin with, you're not going to have any temperature change. So potential temperature doesn't change if you have rising motion when the environmental lapse rate is adiabatic. So if it's stable, that means d theta dz is positive. Rising motion along an adiabatic means potential temperature does not change. Here you're going to cool the column, cool the potential temperature of the column, because the rising motion is bringing up from the surface a constant value of theta along the adiabatic, but the potential temperature is rising with height. So that means the air as it rises has a colder potential temperature than surrounding, and that's going to cool the column, okay? Likewise with an unstable atmosphere, if you have rising in an unstable atmosphere, the temperature of the column is of the rising parcel is going to follow the adiabatic lapse rate or a constant potential temperature. That's going to bring warmer potential temperature up into the column, because the potential temperature is dropping with height. If you have an unstable atmosphere, that's going to warm the column, okay? So depending on if you're talking about potential temperature of temperature, you would think of it differently, but it all makes sense if you just kind of reason out what the effect is and what determine the equation. So remember, vertical temperature change with respect to potential temperature in the potential temperature equation is basically W d theta dz. So when you have d theta dz 0, no temperature change. When d theta dz is positive and you have rising motion, meaning W positive, you have a positive times 5 is negative, so you get cooling. D theta dz being negative, you have rising motion, W is positive, and negative times a positive is a negative, and then negative times negative is positive, you get warming, okay? So just work out the signs, you'll see. So anyway, just think it through, you'll get it. Thank you for listening.